Hello and welcome. I'm so glad you found your way here tonight. Maybe you've had a long day. Or maybe you're simply the kind of person who finds it easier to drift off when there's something quiet and interesting to listen to. Something that gives your mind a soft place to rest without demanding too much of it. Either way, tonight is for you. So let yourself settle in. Let your shoulders drop. Let your jaw unclench just slightly, and let your breathing find its own natural rhythm. Slow, easy, and unhurried. Let your body grow heavy against whatever is holding it, as if the weight of the day is finally releasing, finally being set down. Because tonight, we're going somewhere close, not out into the stars, not across oceans or continents, but inward, into the quiet, extraordinary world of your own mind. While you sleep, your brain doesn't simply go dark. It doesn't pause or idle or wait. It gets to work, cleaning, repairing, sorting, consolidating, and preparing you for tomorrow in ways that are only just beginning to be understood. It does things in the night that it simply cannot do while you're awake, and what it accomplishes in those quiet hours is, in its own gentle way, one of the most remarkable processes in all of biology. So let these soft truths carry you. There's no need to hold on to any of them. Just let them pass through you, like breath, like the last light of evening, like the feeling of finally being still. Your brain has its own dedicated cleaning system. This isn't a metaphor. It's a literal, physical network of channels and fluid that runs through your brain tissue, doing something that scientists only discovered relatively recently, within the last 15 years. It's called the glymphatic system, and most of what it does happens exclusively while you sleep. During waking hours, your brain cells are tightly packed, busy, firing signals constantly, consuming energy, and producing metabolic waste as a byproduct, the same way any active system does. But during sleep, something changes at a cellular level. The spaces between your brain cells actually expand by nearly 60%. This expansion creates room for fluid to flow more freely through the tissue, moving along pathways that are far too narrow to function properly when you're awake and active. This fluid is called cerebrospinal fluid, and it drifts through your brain like a slow and gentle tide. It enters through one set of channels, flows across brain tissue, and exits through another set, carrying waste products with it, flushing the brain the way a slow river might clean a forest floor after rain. One of the most important things this fluid washes away is a protein called beta amyloid. Beta amyloid is a normal byproduct of brain activity, produced throughout the day as neurons do their work. But when it accumulates, when it builds up in the spaces between cells faster than it can be cleared, it forms plaques that have been strongly linked to Alzheimer's disease and cognitive decline. Sleep, in other words, is not passive. It is not simply the absence of wakefulness. It is an active, essential process, one in which your brain performs maintenance that it cannot perform any other time. A good night's sleep isn't just rest. It is, in a very literal sense, your brain cleaning itself. The glymphatic system was identified and named in 2012 by a neuroscientist named Maiken Nedergaard and her team at the University of Rochester. Before that discovery, We had no idea that this process existed. We knew sleep was important, but we didn't know why on this fundamental cellular level. Now we do. And it changes everything about how we understand what happens when we close our eyes. Sleep moves through stages, each one serving a different and important purpose. Your brain doesn't simply switch off. It cycles through distinct phases of activity throughout the night, like a piece of music moving through different movements. The first stage is the lightest. It's the soft edge of sleep, the place where the world begins to grow quiet and your thoughts start to blur and lose their edges. Sounds from the room may still reach you here, slightly muffled, slightly further away. Your body begins to relax, muscle by muscle, and your breathing slows without any effort on your part. In this early stage, your muscles may twitch suddenly, a small jerk that sometimes startles you back to wakefulness for a moment. This is called a hypnic jerk, and it's completely normal. It happens to almost everyone, and it's thought to be a harmless artifact of the transition between states. A small tremor at the threshold between the waking world and sleep. As you sink a little deeper, your brain produces what are called sleep spindles, brief, rhythmic bursts of electrical activity that appear like sudden gentle waves on a brain scan. These spindles play an important role in memory consolidation, helping to stabilize and integrate the things you learned and experienced during the day. They last only a second or two each, but they happen many times throughout the night, quietly doing their work. Deeper still is slow wave sleep, sometimes called deep sleep or delta sleep, named for the slow, rolling brain waves that characterize it. This is the stage where the glymphatic system is most active. This is where the cleaning happens most thoroughly. Your heart rate reaches its lowest point of the night. Your breathing becomes slow and regular, almost like a metronome. Your body temperature drops slightly, as if the whole system is deliberately powering down in order to focus its resources on repair. During deep sleep, the body also releases growth hormone, not just for growing children, but for all of us every night, as a signal for cell repair, tissue regeneration, and the kind of physical maintenance that keeps every system functioning well over time. Deep sleep is when your immune system does some of its most important work. It is, in many ways, the most physically restorative part of the night. And then later, usually in the second half of the night, comes REM sleep, rapid eye movement sleep. This is when most dreaming occurs, when your eyes move gently behind closed lids, as if following something visible only to the sleeping mind, tracing paths through landscapes and conversations and experiences that exist entirely inside you. The brain during REM is nearly as active as it is when you're fully awake. Certain regions actually show higher activity during dreaming than during waking, and yet the muscles of your body are temporarily paralyzed, a state called REM atonia, so that you cannot act out what you're experiencing. This is a quiet and elegant protection, your body kept safely at rest, while your mind moves freely through whatever it needs to process. Dreams in REM sleep tend to be narrative and emotionally vivid. They can feel entirely real. They can carry the texture and logic of waking life, or they can drift into the strange and associative, following rules that dissolve the moment you try to examine them. Most people cycle through 4 to 6 complete sleep cycles each night, with each full cycle lasting roughly 90 minutes. The deepest, most physically restorative sleep tends to come early, in the first 2 or 3 cycles. As the night progresses and morning approaches, the cycles shift, with more time spent in REM and less in deep sleep. This is why the dreams you remember most vividly tend to be the ones closest to waking, in the early morning hours, when REM sleep is longest and richest. Memory is one of the most profound things that sleep protects and strengthens. This is not a small detail. It is central to why sleep matters so deeply. Throughout the day, new memories, things you've learned, conversations you've had, experiences you've moved through, are held temporarily in a structure called the hippocampus. The hippocampus sits deep within the brain, curved and compact, and it functions something like a notepad, holding recent information in a fragile temporary form. During sleep, and particularly during the interplay between slow-wave sleep and REM sleep, these memories are transferred. They move from the hippocampus out to more distributed regions of the cortex, where they can be stored more permanently and woven into the larger fabric of what you know. This process is called memory consolidation, and it requires sleep in a way that cannot be replicated by rest alone. This is why sleeping after studying is more effective than staying awake to review the same material. The brain needs the quiet of sleep to make learning last, to move it from something temporary and fragile into something stable and retrievable. When you sleep after learning something, you wake knowing it more deeply than you did the night before, even without any additional practice. Sleep also strengthens emotional memory, but it does something more nuanced than simply preserving it. During REM sleep in particular, emotional experiences are processed in a way that seems to reduce their sharp edges over time. The memory remains, but the intensity of the feeling associated with it often softens. This is sometimes described as sleeping on something difficult, and the phrase turns out to be literally neurologically accurate. The sleeping brain processes what hurts and gradually makes it easier to carry. This is one reason that REM sleep is so important for emotional regulation. People who are consistently deprived of REM sleep tend to be more emotionally reactive, more easily overwhelmed, less able to modulate their responses to difficult situations. The brain, without its nightly processing time, becomes less resilient. Some scientists believe that dreaming itself may serve as a kind of emotional rehearsal, a space where the brain re-encounters experiences and feelings from a safe distance, finding patterns, testing responses, and gradually integrating what it hasn't yet made sense of. Under this view, even unsettling dreams may serve a purpose. They are the brain doing its work. Not all of your brain sleeps in exactly the same way or at exactly the same time. Different regions move through sleep stages at slightly different rates, and there is a kind of internal variation even within a single night of rest. Some animals take this much further. Dolphins and certain species of migratory birds can sleep with only one hemisphere of their brain at a time, a phenomenon called unihemispheric sleep. One half rests while the other remains alert, allowing them to maintain enough awareness to surface for air or avoid predators. One eye stays open. One side of the brain keeps watch. Humans don't do this in any dramatic or deliberate way. But there are subtle hints that even within our sleep, certain regions of the brain remain more alert than others, quietly monitoring the environment for sounds or changes that might require attention. A parent may sleep through the noise of traffic outside the window, through voices in the hallway, through all the ordinary sounds of a house settling in the night, and yet wake instantly at the soft cry of their child. The sleeping brain is never entirely switched off. It is always, on some level, sorting what matters from what doesn't, keeping a quiet and partial watch over the world. Your brain during sleep is still processing language. If someone gently speaks your name while you're asleep, the language regions of your brain show measurably more activity than they do in response to other sounds. The mind, even at rest, is still oriented toward the things that are most meaningful to it. Body temperature plays a quieter and more important role in sleep than most people realize. Your core body temperature follows a natural daily rhythm, rising through the morning and afternoon, reaching its peak in the early evening, and then beginning to fall as night approaches. This drop in temperature is not just a consequence of sleep. It is one of the signals that helps bring sleep on. The body cooling itself is part of how it prepares for rest. A cooler sleeping environment, somewhere around 18 to 20 degrees Celsius or 65 to 68 degrees Fahrenheit, tends to support deeper and more restorative sleep because it helps the body complete this cooling process more easily. A room that is too warm can interfere with the temperature drop and make deep sleep harder to reach. During deep sleep, the body releases growth hormone into the bloodstream. This happens in a single large pulse, usually in the first few hours of sleep, and it signals cells throughout the body to repair and regenerate. Muscles rebuild. Skin renews. Tissues that were stressed or damaged during the day begin to recover. This is why sleep is so essential, not just for the brain, but for the whole body. It is the time when physical restoration actually happens. The immune system also does significant work during sleep. It consolidates immunological memory, strengthening the body's ability to recognize and respond to pathogens encountered during the day. Studies have shown that people who sleep fewer than 6 hours before receiving a vaccine produce significantly fewer antibodies than those who sleep 8 hours or more. The immune response is partially dependent on sleep, on having the time and the biological conditions that sleep provides. Chronic sleep deprivation is associated with elevated levels of inflammatory markers throughout the body. This low-level, persistent inflammation is linked over time to a wide range of health conditions. Even a single night of poor sleep can raise cortisol levels, the body's primary stress hormone. The following day, making everything feel slightly harder, slightly sharper, slightly less manageable than it might otherwise. A full night of sleep tends to lower cortisol again, gently returning the body to its calmer, more balanced baseline. There is a chemical called adenosine that accumulates in the brain throughout every waking hour, building up steadily as neurons fire and work and communicate. As adenosine levels rise, the feeling of sleepiness grows. This is the brain's natural mechanism for tracking how long it's been awake, a biological pressure that increases with each hour, nudging you gently but persistently toward rest. Sleep clears adenosine away. As you sleep, adenosine is broken down and removed, and by morning, after enough sleep, the pressure has dissipated. You wake feeling refreshed, not simply because you rested, but because a specific chemical accumulation has been resolved. Caffeine works by blocking the receptors in the brain that detect adenosine. It doesn't remove the adenosine or slow its accumulation. It simply prevents the brain from sensing it. This is why caffeine can make you feel alert even when you're tired. But the adenosine continues to build behind the blockade, so when the caffeine wears off, the full weight of it arrives all at once. The tiredness was always there, quietly waiting. Melatonin is the hormone that signals the brain that darkness has come and that rest should follow. It is produced by a small ancient structure deep in the brain called the pineal gland, which is exquisitely sensitive to light. As evening arrives and light fades, the pineal gland begins releasing melatonin into the bloodstream, and the body begins its gentle preparation for sleep. Artificial light, especially the short wavelength blue light emitted by screens and LED lighting, can suppress melatonin production even at low intensities. The brain, encountering this light in the evening, interprets it as daylight and delays the onset of the sleep signal. This is why screen use close to bedtime can make it harder to fall asleep. Not through any dramatic disruption, but through a quiet biological confusion about what time of day it is. Bright light in the morning does the opposite. Even a few minutes of sunlight or bright indoor light shortly after waking helps anchor the circadian rhythm, setting the internal clock firmly for the day and making it easier for melatonin to rise reliably the following evening. The circadian rhythm itself is a remarkable thing. It runs on approximately a 24-hour cycle, regulated by a small cluster of neurons in the brain called the suprachiasmatic nucleus, a name far more complicated than the thing itself, which is simply the brain's master clock, quietly ticking away, coordinating the timing of nearly every biological process in the body. This clock is ancient. It evolved long before electricity, long before artificial light, long before any concept of schedule or bedtime. It is woven into the biology of almost every living thing on Earth, from humans to plants to single-celled organisms. It is one of the most fundamental organizing principles of life. The pineal gland, small as a grain of rice and tucked near the center of the brain, was once a source of deep philosophical fascination. The 17th century philosopher René Descartes called it the seat of the soul, the point where mind and body met, where the immaterial spirit connected to the physical form. He chose it partly because it was the only brain structure he could identify that didn't come in a pair, and he believed the soul must be singular. He was wrong about the soul, but he was right that the pineal gland is singular and important. We now know it as the quiet keeper of our internal night, the structure that responds to darkness and releases the hormone that tells the sleeping brain it's time. Across virtually every animal species that has been studied, some form of sleep or sleep-like rest has been observed. This near universality suggests that sleep is not a luxury or an evolutionary accident. It is one of the most ancient and fundamental biological needs, something that predates complex minds, predates nervous systems as we understand them, predates almost everything we think of as characteristic of animal life. Even jellyfish, creatures with no brain, no central nervous system, no neurons in any conventional arrangement, show periods of reduced activity, reduced responsiveness, and altered behavior that closely resembles sleep. If you disturb a jellyfish during this state, it shows signs consistent with sleep deprivation afterward. Rest, it seems, predates the very structures we associate with resting. Fruit flies sleep. They have preferred sleeping positions. They are harder to wake during sleep than at other times. When scientists kept them artificially awake, they showed memory impairments and shortened lifespans. The need for sleep goes that deep, all the way down to some of the simplest nervous systems that exist. Whales have been observed floating motionless at the surface of the ocean in a behavior called logging, resting quietly in the open water, barely moving, one nostril above the surface to breathe. Some dolphins sleep with one eye open, one hemisphere of their brain resting, while the other maintains enough awareness to surface periodically for air. Some species of migratory birds sleep while flying, in short bursts, a few seconds at a time, one hemisphere at a time, managing to rest during journeys that last days or weeks without landing. The need for sleep is so fundamental that evolution has found ways to accommodate it, even in the most challenging circumstances. As we move through life, the nature of our sleep changes in ways that reflect the needs of each stage. Newborn humans sleep up to 17 hours a day, and most of it is REM sleep. This proportion of REM is thought to reflect the extraordinary neural development happening in those first months, the rapid formation of connections, the explosive growth of a brain that is doubling in size in its first year of life. All of that building and wiring seems to require enormous amounts of the dreaming state. As children grow, the balance shifts. Less REM, more slow-wave sleep. The brain consolidates what it has built, deepening connections and pruning away the ones that aren't being used. Teenagers have a naturally delayed circadian rhythm, a genuine biological shift, not simply a preference or a habit. Their melatonin rises later in the evening and falls later in the morning, making early rising genuinely difficult in a physiological sense. This is a real and measurable phenomenon, and it means that early school start times often work against the biology of the students they're meant to serve. In adulthood, sleep architecture gradually shifts again. The proportion of deep, slow-wave sleep tends to decline with age. Older adults often wake more frequently during the night, not because they need less sleep, but because sleep becomes lighter and more fragmented as the years pass. The need for rest doesn't diminish. Only the ease of reaching its deeper layers sometimes becomes harder. Short naps, when timed carefully, can be genuinely restorative. A nap of 20 to 30 minutes short enough to stay in the lighter stages of sleep without dipping into deep sleep, can restore alertness, improve mood, and sharpen performance for the hours that follow. Longer naps carry a risk. If you sleep long enough to enter deep sleep and then wake from it, you may experience what's called sleep inertia, a period of grogginess and disorientation that can last anywhere from a few minutes to half an hour while the brain surfaces slowly from its deeper state. This is not dangerous, but it can be temporarily unpleasant, and it tends to happen when a nap stretches past 45 minutes. The siesta, a tradition of afternoon rest practiced in many cultures across the Mediterranean, Latin America, and parts of Asia, aligns naturally with a secondary dip in alertness that most people experience in the early to mid-afternoon, regardless of whether they've eaten lunch. This dip is a feature of the circadian rhythm, not a bug. In many ways, the cultures that have built rest into the middle of the day are working with biology rather than against it. Sleep talking is more common than most people realize. It occurs most often during lighter stages of sleep and involves no conscious awareness whatsoever. The words may be clear and coherent or fragmentary and strange, but the person speaking them has no memory of it and no control over it. It is the sleeping brain vocalizing without the waking mind. Sleepwalking is a different phenomenon. It occurs during deep sleep, which is why sleepwalkers can move through complex environments while remaining entirely unconscious. They are not dreaming in the REM sense. The parts of the brain that control movement have become partially activated, while the parts that generate conscious awareness remain deeply asleep. Sleepwalkers are difficult to wake, and doing so abruptly can cause confusion rather than resolving it. Most sleepwalkers remember nothing when morning comes. Night terrors are sometimes confused with nightmares, but they are distinct in important ways. They occur during deep sleep rather than REM, and they typically involve intense physical fear, rapid heartbeat, crying, sometimes screaming, with no associated imagery that can be recalled. The person may appear to be awake and terrified, but they are still deeply asleep. There is no dream, no story, only the raw emotional response. They pass without leaving a memory of content, only sometimes a lingering sense of unease. Nightmares, by contrast, happen in REM sleep and are often vividly remembered. They are narrative experiences with imagery and story and emotion, and they can feel entirely real in the moment. Some researchers believe that nightmares serve a purpose, processing fears, rehearsing responses to threatening scenarios, gradually integrating what the waking mind finds difficult to confront directly. Recurring nightmares about the same theme often diminish over time, as if the brain is slowly working through something, returning to it until it is less charged, less overwhelming. The edges of sleep have long been a source of creative inspiration, a fact that artists, scientists, and inventors have noticed and tried to exploit throughout history. The twilight state between waking and sleeping, called the hypnagogic state, is characterized by a particular kind of loose, associative thinking in which the ordinary constraints of waking logic begin to loosen. The brain produces alpha waves, then theta waves, and thoughts begin to drift and connect in ways that waking logic would typically filter out. Images arise with dreamlike clarity, geometric patterns, faces, landscapes, sometimes vivid enough to seem real. Thomas Edison famously tried to harness this state deliberately. He would nap in a chair, holding a steel ball in each hand. As he drifted towards sleep and his hands relaxed, the balls would fall and wake him, allowing him to capture the ideas and images that arose in that threshold state before they disappeared with deeper sleep. Whether this technique worked as he claimed, it speaks to something real. The recognition that the sleeping and waking mind relate to problems differently, and that the boundary between them can be productive. Salvador Dali reportedly used a similar technique, a key held over a plate falling to wake him at the edge of sleep, and credited the hypnagogic state with the imagery in his surrealist paintings. Paul McCartney said the melody for Yesterday came to him fully formed in a dream. He woke with it in his head, found his way to a piano, and played it immediately. He was so convinced it was something he must have heard before that he spent weeks asking other musicians if they recognized it before finally accepting that it was his own. The chemist Auguste Kekulé described dreaming of a snake biting its own tail, the Ouroboros, an ancient symbol, and waking with the insight that the molecular structure of benzene was a ring, a discovery that transformed organic chemistry. Whether the story is precisely accurate or embellished in the retelling, it reflects something real about how the sleeping mind approaches problems differently, finding solutions that the systematic waking mind might miss. The brain produces distinct electrical rhythms at different stages of sleep, and these rhythms can be measured, mapped, and studied with remarkable precision. Delta waves are the slowest, large, rolling, unhurried waves that appear during the deepest stages of sleep. They are associated with the most restorative rest, the kind where you wake feeling genuinely renewed. Theta waves appear in lighter sleep and in the drowsy transition between waking and sleeping, a softer, more fluid rhythm that carries the mind in and out of awareness. Alpha waves tend to appear just before sleep, when the eyes are closed and the body is relaxed, but the mind is still gently present. The quiet, comfortable place between alertness and drift. Measuring these waves has given scientists a window into the sleeping brain that would have seemed impossible a century ago. We can now watch in real time as a sleeping person moves through stages, consolidates memories, processes emotions, and clears the metabolic debris of the day. The sleeping brain, once assumed to be simply resting, turns out to be extraordinarily active, just active in a different way, oriented toward different tasks. The relationship between sleep and mental health is deep and reciprocal. Poor sleep contributes to anxiety and depression, and anxiety and depression contribute to poor sleep. A cycle that can become self-reinforcing if left unaddressed. But the relationship goes even deeper than this. REM sleep seems particularly important for emotional processing. Studies have found that people who are selectively deprived of REM sleep, allowed to sleep, but woken whenever they enter the REM stage, show increased emotional reactivity, reduced empathy, and greater difficulty managing stress. The brain, without its nightly emotional processing time, becomes less flexible, less resilient, more easily overwhelmed by the ordinary difficulties of being alive. Conversely, people who sleep well tend to have better emotional regulation, more stable moods, greater capacity for patience and perspective. Sleep doesn't solve problems, but it consistently makes them easier to navigate. The phrase "sleep on it" turns out to be, neurologically speaking, genuinely good advice. The brain's prefrontal cortex, the region most responsible for reasoning, decision-making, impulse control, and emotional regulation, is particularly sensitive to sleep deprivation. Even a single night of insufficient sleep measurably reduces prefrontal activity and increases the reactivity of the amygdala, the brain's emotional alarm center. The result is a mind that reacts more and reasons less, more easily triggered, less able to modulate its own responses. And yet the brain is remarkably resilient. Several consecutive nights of adequate sleep can begin to restore what sleep deprivation has diminished. The recovery is not instant. Some effects of chronic sleep loss take longer to reverse. But the brain is always ready, given the opportunity, to begin healing. It is oriented toward restoration. It wants to repair itself. Sleep is how it does it. There are things you can do to make sleep easier, and most of them are quieter and gentler than they might sound. Keeping a consistent wake time, even on weekends, even after a difficult night, is one of the most effective ways to stabilize the circadian rhythm. The brain learns from repetition. It anchors its internal clock to the reliable rhythm of the same morning hour. And over time, this makes falling asleep easier, makes sleep deeper, and makes mornings feel more natural. Writing down worries or a to-do list before bed, simply offloading the contents of your mind onto paper, has been shown in research to reduce the mental activity that keeps people awake. The brain, knowing that something has been recorded, is often able to let it go. The act of writing is a kind of reassurance. This will not be forgotten, so it does not need to be held onto right now. A warm bath or shower taken about an hour before bed can gently support the body's natural temperature drop. The warmth draws blood to the skin's surface. When you step out into cooler air, your core temperature falls slightly, and this drop signals to the brain that sleep is near. It is a small intervention, but it works with the body's own biology rather than against it. The scent of lavender has appeared in multiple sleep studies as a gentle aid, associated with slower heart rate, slightly lower blood pressure, and improved subjective sleep quality in some people. Not dramatic, not universal, but present. The sense of smell connects directly to the limbic system, the brain's emotional center, which is perhaps why certain scents can have such an immediate and physical effect on how we feel. Magnesium, found in foods like almonds, dark leafy greens, seeds, and dark chocolate, plays a role in regulating several neurotransmitters involved in relaxation and sleep, including GABA, which quiets neural activity. Many people don't consume enough of it. Alcohol is worth mentioning honestly. It can make falling asleep easier, it reduces anxiety and promotes sedation, but it fragments sleep architecture throughout the night. It suppresses REM sleep, increases the likelihood of waking in the second half of the night, and leaves the brain less restored by morning than it would have been without it. The sleep that alcohol enables is lighter and less complete than natural sleep. Exercise, on the other hand, consistently supports deeper and more restorative sleep over time. Even moderate activity, a daily walk, a gentle stretch, time spent moving through the world, is associated with longer, slow-wave sleep, better sleep efficiency, and improved sleep quality in study after study. The body that has been active tends to seek rest more genuinely. There are things about the sleeping brain that remain genuinely mysterious. Places where the science stops and the wondering begins. We still don't fully understand why we dream. We have good theories: emotional processing, memory consolidation, threat rehearsal, pattern recognition. But no single explanation accounts for everything. Dreams can be mundane or bizarre, emotionally resonant or entirely abstract, connected to recent experience or drawn from the remote past. They follow their own internal logic, which dissolves the moment you try to examine it. They can feel more real than waking life and be forgotten completely within minutes of opening your eyes. Some people remember their dreams vividly and regularly. Others rarely or never recall them, though research suggests everyone dreams whether they remember it or not. The difference seems to lie in how deeply you wake between sleep cycles. Those who wake briefly in the night, even for just a moment, are more likely to carry a memory of the dream that preceded that waking into consciousness. We don't fully understand why certain people sleepwalk, or why night terrors occur, or precisely what determines the emotional tone of dreams. We don't know exactly how the glymphatic system is regulated, or whether certain sleep habits affect its efficiency more than others. We don't know whether it's possible to enhance the brain's nightly cleaning through anything other than simply sleeping longer and more deeply. These mysteries are not failures of science. They are invitations, open questions at the edge of what is known, waiting for the curiosity and patience of future researchers. There is something worth knowing about the relationship between sleep and learning that goes beyond simple memory consolidation. Something subtler and, in its way, more beautiful. When you sleep after encountering a new skill, a new piece of music, a new language, a new movement pattern, the brain doesn't simply store what you practiced. It continues to work on it. Connections that were just forming when you went to sleep are strengthened and refined during the night. Pathways that were inefficient become smoother. In the morning, you are often measurably better at the skill than you were when you stopped practicing. Not because you've practiced more, but because your sleeping brain has quietly optimized what you already did. Musicians and athletes have long known this intuitively. There's a reason coaches say to sleep on a difficult passage, to give a hard movement a night before trying it again. The sleeping brain, freed from the moment-to-moment demands of execution, can take a broader view, smoothing, integrating, making the learned thing more natural and more deeply embedded than waking practice alone could achieve. This process happens with language too. People learning a new language who sleep after study sessions show better retention and faster progress than those who stay awake. The sleeping brain seems to find the underlying patterns in what it's been given, extracting the grammar, internalizing the rhythms, making the foreign feel more familiar by morning. And it happens with problem solving. There is a well-documented phenomenon, sometimes called the sleep effect on insight, in which people who sleep between 2 attempts at a difficult problem solve it more often than those who stay awake between attempts. The sleeping brain approaches the problem differently. It makes connections that the focused, sequential, waking mind tends to miss. It finds the shortcut, the unexpected angle, the solution that becomes obvious only when you stop trying so hard to find it. The environment in which you sleep shapes the quality of what your brain can do during those hours. Light is perhaps the most powerful environmental factor. Even small amounts of light during sleep, a street light through a curtain, the glow of a phone screen, can suppress melatonin and shift the brain toward lighter sleep stages. Darkness signals safety to the ancient parts of the brain. It permits the kind of deep relaxation that light, even dim light, tends to prevent. Sound matters too, though in a more complex way. Complete silence isn't necessary for good sleep, and for many people, consistent ambient sound actually helps by masking the irregular intrusions that tend to cause waking. What disrupts sleep most is not volume, but variability. A sound that changes suddenly, that breaks a pattern, that demands attention. This is why a car alarm wakes you when traffic doesn't. Why a partner's irregular snoring is more disruptive than a fan running steadily. Temperature, as mentioned earlier, has a measurable effect on sleep architecture, but so does the simple comfort of feeling safe, the perception that you are in a secure place, that nothing requires your vigilance. The nervous system, particularly the autonomic nervous system that regulates arousal and relaxation, responds to environmental cues that signal either danger or safety. A room that feels comfortable, familiar, and secure allows the nervous system to settle in ways that a tense or unfamiliar environment doesn't. This is one reason that sleeping in a new place, a hotel room, a friend's house, somewhere unfamiliar, is often lighter and more fragmented than sleeping at home. Researchers call this the first night effect. One hemisphere of the brain stays in a slightly more alert state when the environment is new, as if keeping partial watch while the other hemisphere rests. It is the same instinct that keeps a sleeping animal from fully letting go in exposed or unfamiliar terrain. Over time, the brain associates your sleep environment with rest itself. The bedroom, the pillow, the particular quality of darkness and quiet, the familiar sounds of the house. All of these become cues that signal the brain it is safe to let go, that rest can begin. This is why sleep specialists often emphasize keeping the bedroom for sleep, because the association between that space and rest is itself a resource, something the brain can use to settle more quickly and more deeply. There is a concept in sleep science called sleep pressure, and it's a useful way to think about why sleep works the way it does. Sleep pressure is the biological drive towards sleep that builds throughout every waking hour, driven primarily by the accumulation of adenosine. The longer you've been awake, the higher your sleep pressure, and the stronger the urge to rest. This pressure is one of the two main forces that regulate when you sleep, the other being your circadian rhythm. which determines when you're biologically primed for sleep, regardless of how long you've been awake. These two systems usually work together. By late evening, after a full day of waking, your sleep pressure is high and your circadian rhythm is guiding you toward rest simultaneously. Both forces align and sleep comes easily. But when they fall out of alignment, when you've napped late in the day and reduced your sleep pressure, or when you've traveled across time zones and your circadian timing is off, sleep becomes harder to find, lighter when it comes, and less restorative. Understanding this helps explain why certain sleep strategies work. Going to bed at a consistent time takes advantage of circadian alignment. Avoiding long naps late in the day preserves sleep pressure for the night. Spending time in bright light in the morning anchors the circadian clock. Each of these practices works with the body's existing systems rather than against them. Sleep debt, the accumulated shortfall from nights of insufficient sleep, is real, though it is somewhat more complicated than a simple bank account. You can recover some of what was lost with subsequent nights of good sleep, but the recovery isn't always complete or straightforward. Some effects of chronic sleep deprivation persist even after apparent recovery. The brain's sensitivity to sleep loss and its capacity for recovery varies between individuals in ways that are partly genetic. Some people genuinely function well on less sleep than others, not because they've trained themselves to need less, but because of differences in how their brains process and respond to sleep pressure and to the biological effects of sleep loss. This genetic variation is real, though it is also frequently overstated. True short sleepers, people who genuinely thrive on 6 hours or fewer, are quite rare. Most people who believe they've adapted to little sleep are in fact functioning below their optimal capacity without fully realizing it. The brain is not always a reliable judge of its own impairment. Across cultures and throughout history, sleep has been surrounded by ritual and meaning in ways that suggest people have always sensed, even without scientific language for it, that what happens in sleep is important. Ancient Egyptians believed that dreams were messages from the gods, delivered during the vulnerable hours of sleep when the soul was closest to the divine. They had dedicated dream temples, places people would go to sleep in hopes of receiving guidance, healing, or prophecy through their dreams. The Greeks had Hypnos, the god of sleep, and his son Morpheus, the god of dreams, figures gentle enough to bring rest, powerful enough to shape what the mind encountered in that rest. Sleep was understood as a kind of travel, a nightly journey to a realm adjacent to the waking world, but operating by different rules. Across many indigenous traditions, dreams are considered a form of perception, not imagination, but a genuine way of knowing, receiving information that the waking mind cannot access. The content of dreams is taken seriously, considered, discussed, integrated into the decisions and understanding of waking life. Modern science has largely set aside the question of what dreams mean in any spiritual or prophetic sense, focusing instead on their neurological function. But the ancient intuition that something significant happens during sleep, that the resting mind has access to something the busy, waking mind does not. Turns out to be, in a very different way, entirely correct. Sleep is not nothing. It has never been nothing. We just now have different language for what it is. Your body, right now, knows what to do. Your breathing has found its rhythm. Your muscles are releasing, one by one, the small tensions they carry through the day. Your heart rate is settling toward its nighttime pace. The temperature at your core is beginning its slow and gentle fall. The glymphatic fluid is moving. The adenosine is clearing. The memories of today are beginning their long, quiet journey toward permanence. You don't need to think about any of this. You don't need to understand it, or direct it, or even believe it. It will happen regardless, because this is what your brain and body do when you give them the chance. This is what they have always done. This is what they were made for. The thinking can stop now. The planning can wait. The worrying has nowhere useful to go in the dark, and you can pick it up again in the morning if you still need it. Though often, after a full night of sleep, the things that felt enormous in the evening feel smaller and more manageable by morning. That's not a coincidence. That's the brain doing its work. So let the words fade now. Let the voice grow quieter. Let whatever thoughts are still moving through your mind slow down and drift apart, like clouds pulled gently by a wind you can't feel. You are safe. You are stilled. You are exactly where you need to be. Rest well. Good night. Right now, as you rest, something remarkable is happening. The fluid is moving through your brain, slowly, gently, doing the quiet work of clearing away the residue of the day. Your neurons are replaying the events of the last several hours, marking some for preservation, releasing others, weaving new threads of memory into the fabric of what you know. Your immune system is strengthening. Your body is repairing. The stress of the day is being metabolized, its edges softened, its weight distributed into something more bearable. Your brain is doing what it was made to do. It is taking care of you. You don't need to help it. You don't need to think about it, or direct it, or understand it. All you need to do is exactly what you're doing right now. Lying still, breathing slowly, letting the day go. The brain already knows what it needs to do. And so does the rest of you. You are safe. You are still. The world outside can wait until morning. The list and the worries and the things that felt urgent only hours ago, they will all still be there tomorrow, and you will be better equipped to meet them after a full night of this quiet, extraordinary repair. Let your eyes stay closed. Let your breath stay slow. Let the words fade into the background of your awareness, softer and softer, like a voice heard from another room, like the sound of rain on a roof far away. Rest well. Good night.